Today we are going to talk about water source heat pump systems. And this is the last module in the water side, or excuse me, the last lecture and homework assignment for the water side systems module. So water source heat pumps. Earlier in the semester, we talked about air source heat pumps, which an air source heat pump is a system that can provide both heating and cooling via a refrigeration cycle. And it does that by either rejecting heat to the outside or absorbing heat from the outside, depending on which mode it's operating in. Water source heat pumps, which are often abbreviated WSHP, they are doing effectively the same thing, but these are a bit more similar to a water source chiller. So back when we talked about water source chillers versus air source chillers, water source heat pumps are a little more aligned with a water source chiller setup. Instead of dumping or absorbing heat from the outside air, these are instead dumping or absorbing heat from a common water stream, which we call condenser water. And if you think back to when we talked about chilled water systems, it's the same exact term we used back then. So chilled water systems, specifically water source chilled water systems, also have a condenser water loop. Water source heat pump systems also have a condenser water loop, but the configuration is a little bit different, which we'll get to here in a minute. In this type of system, each water source heat pump can provide heating or cooling to whatever space that it serves. So every zone in your building would have a dedicated heat pump that can provide heating or cooling. If our thermostat says we want heat, what the heat pump will do is pull heat from the condenser water, use that to heat up the supply air, and then send that out into the space. And then conversely, if our space wants cooling, then the heat pump will reject heat into the condenser water. And it'll cool down the supply air as it does that, and then send cold air into the space. So we're still either heating up or cooling down the airstream. And to do that, we are moving heat energy from the air to the water. Here is a basic schematic of what a water source heat pump system would look like. We have our water source heat pumps out in the building. In this case, I'm showing 4 distinct units. So each one of these would have a dedicated thermostat. But in a typical water source heat pump system, you're probably going to have at least 20 heat pumps, could be 100 heat pumps, just depends on how big the system is. If you only have 4 zones, it's probably not going to warrant a water source heat pump system. But anyway, so we have our heat pumps here on the right side. We have our condenser water supply, which we're sending out into all of our heat pumps with our solid black lines here. It goes into each heat pump's DX refrigerant coil, and then it's going to come back as condenser water return. We have our condenser water pump that's going to make sure the water's flowing through the system. And then we have a boiler. And so you can see, if you follow the pipe schematic, water can either go to the boiler or it can bypass the boiler. And then we also have a cooling tower or a fluid cooler, which, similar to the boiler, we can either send water into the tower or we can bypass it. And note the condenser water supply is going to be somewhere in the range of 50 to 80 degrees. If you think back to when we were talking about hot and chilled water systems, those systems had a much tighter temperature band on the water we're sending out and um, and returning, this has a wider temperature band to it. And I'll explain that here in a moment. A water source heat pump, this is what it would look like out in the wild, and then somewhat of an exploded view on the right. So we're going to bring in our air into the unit. You can see we have a filter right here. We always want to filter our air coming into the unit so that we can protect the coils that are in the heat pump or the air handler and just collect all that dust before it collects on the coil itself. And then out the top of this thing, we're going to have either hot or cold air that we're going to send out into the room. We have our condenser water in and our condenser water out. And then looking at the exploded view here, what they're calling a refrigerant to air heat exchanger, that is really our DX coil that's in the airstream. So as this fan turns, you can see the fan impeller kind of sticking out here. That's going to draw air through this coil, and it's actually just going to pass over all this other stuff in here, our compressor and all these other components. And then we also have our refrigerant to water heat exchanger. And it's through that we are transferring heat energy with our condenser water loop. So if this unit is in cooling mode, it's rejecting heat into the water through this refrigerant system. If this is in heating mode, it is pulling heat out of the condenser water system to then deliver into the space. I mentioned that condenser water loop. It's always going to be somewhere in that 50 to 80 degree Fahrenheit range. If that loop temperature starts to fall below 50 degrees, so in this case, that is our what we call the low limit. That's the low limit of this range. If we start to fall below 50 degrees, that boiler that we saw in that system schematic, that boiler will kick on and heat the water a bit to maintain that minimum 50 degree temperature water. But this should only happen if most or all of our heat pumps are in heating mode and they're all pulling heat out of the water. If all of your heat pumps are in heating, they are extracting a lot of heat out of the water to then deliver into your space. And that means your water temperature will start to drop. On the opposite end, let's say our condenser water temperature starts to rise above 80 degrees, which is our high limit on this. In that case, our cooling tower is going to kick on to maintain a maximum temperature of 80 degrees, meaning we don't want the temperature to get warmer than that. And this should only happen if most or all of our units are in cooling mode, which means they're rejecting a lot of heat into the loop. They're pulling heat out of the spaces and then putting it into the condenser water, which is going to warm up that condenser loop. And then the third scenario, well, what if our condenser water temperature is between our high limit and our low limit? So let's say it's just cruising at 65 degrees Fahrenheit. In that case, our boiler and our cooling tower, they don't need to do anything, and they are just going to remain off. There's going to be this constant trade-off of some heat pumps are in heating mode, some heat pumps are in cooling mode throughout your entire building. And if you think back to when we were talking about VRF systems, this is going to start sounding very familiar. The biggest benefit of this type of system, any energy pulled from a water source heat pump in cooling mode can be used by a heat pump in heating mode. So again, like VRF systems, a water source heat pump system is able to trade energy around the building. Instead of a refrigerant network like in VRF, this is all connected with a condenser water network, so to speak. So they're just able to move energy around the building whenever you have these units in competing mode. It's not free though. It's not quite as good as VRF. VRF isn't quite free either to trade this energy around, but VRF would be better than water source heat pump. And the reason it's not free is to move that heat energy from the water to the air, or vice versa. We still have to run a bunch of compressors. So even if all of our heat pumps are in perfect balance between heating and cooling mode, we still have to run a compressor at every single one of those heat pumps. So it's not free to do that, but it still is very efficient. If you end up in one of the extremes, so let's say every single heat pump is in heating mode, and every heat pump is pulling heat from the condenser water. Well, what that means is your boiler will need to turn on and essentially provide full heating to your building. In this scenario, you're not gaining any efficiency on the trading of energy because they're all in heating mode. They're all pulling heat out of the water, which means your boiler has to make up that energy 100%. And the important note here is now you're paying a penalty to transfer that heat energy using your DX coils. Because, like I said, we still have to run all of these compressors on top of running our boiler at full fire. And so now we have this penalty we pay. And that means this is actually going to use more energy than a straight gas-fired hot water system. Because in a hot water boiler system, you're producing all that heat at the boiler, pumping it out to the coils, and then the heat transfer just happens right there at the coils directly, versus a heat pump system where you're heating up the condenser water and then you have to still run all these compressors to extract that heat out of the condenser water. But how often would that actually happen? Probably not super often. It depends on your building layout, how it's zoned. Um, but you could have scenarios or certain building layouts where you do have these scenarios where all of your units are going to be in heating mode. On the opposite end, if all of our heat pumps are in cooling mode, they're all rejecting all of this heat into the condenser water. Now we have to run the cooling tower to provide full cooling to the building. But if we're in the sweet spot where half are in cooling, half are in heating, then we have this nice balance of heat pumps just moving energy around the building, and the boiler and the cooling tower just get to turn off and not do anything. Our typical operating conditions in a heat pump system are pretty much always somewhere in between full cooling and full heating. So it's kind of like keeping a balance sheet. So you have some heat pumps that are pulling energy out, some heat pumps putting energy back in, and then the balance needs to be handled by the boiler or the cooling tower. So again, think back to VRF, where on your homework assignment, you essentially tabulated a balance sheet of some fan coils are in heating and some are in cooling. What's the net balance at the end of the day? And then what needs to happen at the heat pump to serve that resultant load? So it's a similar idea here. To drive the point home, let's visualize it. We have our heat pump system, and let's say every single one of these units is in heating mode. So they're all extracting heat out of the water and then delivering warm air into the space. Our condenser water return, let's say it's coming back around 45 degrees, which means we have to turn on our boiler, heat it up to that minimum of 50. Our cooling tower is off. and then we'll supply 50-degree water back to the heat pumps where the heat gets extracted again, and then it just continues that cycle. In cooling mode, if we have all of our units in cooling, they're all rejecting heat and then supplying cold air to the space. Our condenser water return, let's say that's around 90 degrees, so it's getting pretty warm. That's above our 80-degree limit. So in that case, we don't need our boiler, but we do need to turn on our cooling tower, which will then reject heat to the outside and then cool that water back down to 80 degrees and then send that back out to the heat pumps where the cycle starts over again. So those would be the extremes. And then if we have a nice balance of some of these are in heating mode and they're pulling heat out, some are in cooling mode, they're putting heat back in, we end up with this nice balance where both our supply and our return are somewhere in that 50 to 80 degree range. That's the sweet spot, which means our boiler's off, our cooling tower's off, and we're just trading energy around the building. These compressors that are in all these heat pumps, we've talked about this in the past, but this is a good time to come back to it. These compressors, they take electrical energy, and that energy will end up in the refrigerant. It's just like if you have a fan that's moving air or a pump that's moving water, all of that input energy into those systems ends up in the fluid. In this case, the fluid is our refrigerant. In cooling mode, the compressor heat will end up in the water stream because that is where we are rejecting our heat. So if our compressors are producing heat, ultimately that will get rejected into the condenser water stream. But in heating mode, this compressor heat will end up in the air stream because that's where we're rejecting heat in that process. We're trying to heat up the air. So why not let that compressor heat go into the air and actually do something useful? What this means is the compressor heat actually hurts our cooling process a bit because now we're cooling the compressor heat as well as the space cooling needs. If our space needs to reject 50,000 BTUs per hour, well, now we have to move 50,000 plus whatever that compressor heat is. In heating mode, though, that actually helps. If you think back to your thermodynamics process or class, you probably learned that your heating COP is always going to be greater than your cooling COP. And this is why, because that compressor heat is actually helpful in heating mode. So whenever our heat pump is in cooling mode, here's our basic schematic. This is kind of a review from one of the first lectures we did. So we have our room sitting at 75 degrees, and we're going to have this Q removed, the amount of heat we're removing from the space. We have our electrical input going into our heat pump to make this thing happen. And then ultimately, the sum of those two things are going to get rejected into the condenser water. So our space heat removed plus our compressor heat. So the total heat rejected to the condenser loop will be a combination of those two things. To put that in equation form, if we're in cooling mode, the heat going into the condenser will be equal to the heat removed from the space plus the compressor heat, which would be the Q removed divided by whatever your COP is. Quick example, let's say we have a heat pump that has a 4.0 COP in cooling. And our space cooling load at this moment in time is 120,000 BTUs per hour. So that's how much heat we need to remove from the room to keep that space happy. And let's say I want to know how much total heat are we putting into the condenser water as a result of this. Quick equation, 120,000 plus 120,000 over 4. That first term is the heat we're pulling from the space. The second term is our compressor energy that's required to move that 120,000. And so we're ultimately going to add 150,000 BTUs per hour to the condenser water. But now this energy can be used somewhere that actually wants that heat. And this illustrates the idea that there's this penalty you have to pay in cooling mode. I really only want to move 120,000. But in order to move 120,000, I have to reject 150,000. In heating mode, the schematic is reversed. So now we're pulling heat from the condenser water. So that's our Q condenser here, just the signs would be different. We still have our electrical input, and now our Q delivered, our useful heat that we're delivering into the room will be a sum of those two things, the heat removed from the water plus our compressor energy. So very similar idea, we're just essentially mirroring the process. In equation form, the Q delivered into the room will be the condenser water energy we've taken out plus our compressor heat. But let's take that equation, and I want to solve for the Q on the condenser side. Because when we looked at this in cooling mode, that's what we looked at, because we wanted to know how much heat we were rejecting into the water. In this case, I want to know how much heat are we taking out of the water. So do some quick hand calcs to solve for Q condenser, and you end up with this. So the total heat that we are taking out of the water will be the Q we need to deliver divided by 1 plus 1 over our COP in heating. So if we know what our space heating load is, if we know how much heat we need to deliver to our room to keep that space happy, now we can figure out how much energy we need to pull out of the condenser water to actually deliver that. Another example, let's say our heat pump has a 3.0 COP in heating mode and our space heating load is 100,000 BTUs per hour. And I want to know how much heat do we need to pull out of the condenser water to serve that load. Plug it into this equation I just gave you. So if we know we need to deliver 100,000, and then we have our condenser water terms over here, or you could just start with the version of this where the condenser term is what you're solving for. But this 100,000 is our total heat output. And then we have our heat we're pulling from the water plus our compressor input energy that's required to move that Q condenser. And if you solve for that, you find out you need to pull 75,000 BTUs per hour out of the condenser water. But even though you've only pulled 75,000 out, you still get 100,000 delivered as your useful output. And now this keeps the water a bit colder because we've taken 75,000 BTUs per hour out. And if there are other heat pumps in the building that actually want to cool their spaces, this helps them. To sum it up into one nice easy slide, if you have a heat pump in cooling mode, if you have a heat pump in heating mode. And just keep in mind that the delivered and removed in those equations, that's in relation to the heat transfer from or to the room or space, because that is our useful output. In a cooling system, the useful output is how much heat did I remove from the space, because that's really how much air conditioning you're getting, at least useful air conditioning. The Q delivered in heating mode, how much total heat did I deliver into the space? That's the useful output in heating mode. So you look at all the heat pumps in your system, some are in heating, some are in cooling, then you figure out the balance. And to put that another way, am I overall losing or gaining heat in the loop? If more of my heat pumps are in heating mode, that tells me my boiler is going to have to kick on and pick up the slack, because we're starting to fall below 50 degrees or whatever our low limit happens to be. And so our boiler has to kick on to serve that. But if more of them are in cooling mode, then the cooling tower is going to have to do the same thing to maintain that high limit. But again, if we're in the middle, or if maybe we're only slightly skewed to heating or cooling, maybe the boiler just has to kick on once every hour or once every couple hours, or vice versa on the cooling tower. So that's the bread and butter of water source heat pumps. They've been around for a long time. This isn't new technology. We don't see them super often because they are a pretty expensive system, but it is kind of a neat idea. And like I said earlier, VRF systems are kind of doing the same thing, just with a refrigerant network instead of a water network. One variation on this is what's called a ground source heat pump system, which is often abbreviated GSHP. With a ground source heat pump system, the building side looks exactly the same. So you still have all of your heat pumps throughout your building, and they're probably the exact same heat pumps you would buy with a standard water source heat pump system. So that side looks identical. You still have a pump that's moving water through your building, but the big difference is there's no boiler or cooling tower. Our condenser water is instead trading energy with the earth itself. The reason it can do this is our soil temperatures stay relatively stable all year round. Whether it's the peak of summer or the peak of winter, our soil temperatures, once you get below, I want to say about 10 feet or so, they are a nice consistent 50 to 55 degrees Fahrenheit, regardless of season. And that temperature range, 50 to 55, that is awesome to use as either a heat sink or a heat source, depending on what your heat pumps are doing. If your heat pumps are all in cooling mode, then 50 to 55 degree soil is a good temperature to dump that heat energy. It's cold enough to do that. Or it's also warm enough to use as a heat source if we need to pull heat out of the earth when we're in heating mode and we actually need to heat our building. So the principles here on the water source heat pump side of things are identical. The only difference is if the system's not in balance, where is that extra energy coming from? In a water source heat pump system, that makeup energy is coming from a boiler and a cooling tower. In a ground source system, that makeup energy is coming from the earth. There are two fundamental types of ground source heat pump systems. You have what's called a closed loop. I'd say this is probably the more common of the two. And this is a completely closed piping system. And so you put your pipe deep into the earth, and as your water runs through those pipes, it trades heat energy with the earth just by contact of the pipe. Well, contact of the water to the pipe to the earth. As opposed to an open loop, where our piping system is open to some kind of water source. In an open loop, we're actually drawing water in on one end, running it through our through our building systems, and then we are pumping that water back in to whatever that water source was. One thing of note, ground source heat pump systems are not geothermal systems. This is a common misconception that drives me up the wall a little bit. I've also heard them called geothermal heat pumps, which is not really the right term. These are not geothermal systems. Geothermal systems pull heat energy directly from hot springs or volcanic activity. That is a geothermal systems. True geothermal systems don't use heat pumps, and they are by nature heating only systems because they're using the heat energy from hot springs or whatever they can find this heat energy from. That is a geothermal system, but ground source heat pumps are not geothermal systems. Ground source systems are also commonly mislabeled as renewable energy systems, which again drives me up the wall. That is a factually incorrect statement. These are not renewable systems, even though we're using the heat energy of the earth to either heat or cool our buildings. The reason they're not renewable is we still have to run all of these compressors. In our McKinstry building, we have a closed loop heat pump system and probably, I would guess, 20 to 30 heat pumps, which means we have 20 to 30 compressors that we need to run in order to shift that energy around. And by that effect, these are not renewable systems. Those compressors still take energy to run. So this is not free, but it is very efficient. This is probably one of the most efficient HVAC systems you can get, but it is not renewable. This is a basic, very basic schematic of what these systems look like. If you have a closed loop, there are some different ways you can do it. This would be a horizontal loop where you don't run your piping very deep in the ground, but you run it very long in lateral directions. So the downside here is this requires potentially a lot of land to bury all this pipe. And you do have to space out your piping to a certain degree, because if you space your piping too close together, and then you go through a whole season where most of your heat pumps are in heating mode, you will actually start to depress the temperature of the soil over time to the point where it could become a problem. And so to address that, they do space the piping out a certain degree to try to minimize that. Or on the other side, if you're in summer, then you're rejecting a bunch of heat into the soil, and that could raise the temperature of the soil over time. So that would be a horizontal loop, or you can do a vertical loop, which doesn't take nearly as much land, but now you're just going much, much deeper. And when I say deeper, I'm talking potentially hundreds of feet straight down into the ground. But same idea, closed loop. So your water is just in contact with the soil, either heating or cooling. This third variation, it's using a water source to provide better heat transfer, but it is still a closed loop system. And then finally, this last variation, this would be an open loop. So we can see we would be pulling in water on one side of this. using it in our building for heating or cooling, depending on what we need, and then sending that water back into the water. This is a lot more complicated. I've never designed an open loop system, but I've heard lots of horror stories of heat exchangers just getting plugged up in record time, or environmental agencies. You have to convince them that you're not going to cause any issues with your open loop system. But if the conditions are right, that's a potential option. The good thing about the open loop is, and it's kind of represented here, you need a lot less piping. In all of these closed loop systems, you need a lot of contact time between your water and the earth to get whatever cooling tonnage you need for your system. You need a lot of pipe to do that because of its closed loop nature. In an open loop setup, you don't need all of that because you're just pulling in the water directly. You just need to make sure you can get whatever gallons per minute you need to serve your building. If we're talking about efficiency, ground source systems are a lot better than water source heat pumps. Reasons being, on the makeup energy side, we don't need a boiler, we don't need a cooling tower, so there's a lot less energy on the makeup side of the equation. All you really need to do in a ground source system is run a pump and just get that water moving, and you're just pumping the water through the earth. That's it. You might need a bigger pump if you have an extensive piping network underground, but at the end of the day, that's going to be way more efficient than having to put in a boiler and a cooling tower. On the cooling COP side, ground source is typically much better because we're usually dealing with lower condenser water temperatures. A ground source system will typically have a condenser high limit of around 65 as opposed to 80 in a more traditional water source heat pump system. And so if you think back to the lift, the concept of how hard does my compressor need to work in my DX system, if you have lower water temperature, that means it's easier to reject heat when we're in cooling mode. If we can keep our condenser temperature lower, that means our cooling efficiency will be better because that's a lower evaporator temperature. On the heating side, it's roughly similar heating COP in both system types because both of these systems usually have a similar condenser low limit of 50 degrees. So if both of the systems are only maintaining about 50-degree water as their low limit, the heating COP is going to be essentially the same. The last point, and then I'll let you go, this idea of backup heat. So this is the last benefit to talk about, another reason why these systems are pretty nice. If you have a water source heat pump or ground source system, then we don't need backup electric or gas heat like we do on air source heat pump systems. So remember, when we talked about air source heat pumps, we talked about how as it gets colder outside, we lose heating capacity, eventually to the point where we often need a backup heating source because our heat pump capacity will drop below the load of the space. For a water source or ground source system, we don't need those backup heating sources, except, important note, the boiler makeup heat. But that's a little bit different in how we're describing backup heating systems. So the reason we don't need it with these types of systems is our condenser water temperatures are always at a stable place. They're always in that range of, say, 50 to 80 degrees. It doesn't matter how cold it is outside, the condenser water temperatures are always stable. And so the heat pump capacity will not go down as outside air temperatures get colder, because our heat pumps aren't really looking at outside air temperatures. They're looking at what is the condenser water temperature, because that's where they are rejecting the heat. They don't care about outside air. They just care about the condenser water. Versus air source systems typically have way more extreme heat sink or heat source temperatures. Because it's using outside air conditions, you're in that 0, potentially down to 0 degrees Fahrenheit in Spokane, at least, or in cooling mode, you could be at 100 degrees. Water source heat pumps, by comparison, they're always going to be nice and stable because our loop temperature is always in that 50 to 80 degree range, regardless of the outside air temperatures. That's all I got for you today. Any questions on that? Awesome. I'll stick around for 20 minutes or so if anybody has homework questions, but otherwise, I will see you all on Thursday.